sounds, they look just the same.
Good morning, I'm Jess Jean. I'm the Chief Scientist for Nuclear Science and Technology at Idaho National Laboratory. I'm also the Acting Division Director for our Advanced Scientific Computing Division, which we just formed a couple months ago.
Tell us a little bit about that.
So we believe advanced computing plays a big role in our development of nuclear energy. At this site we have a lot of physical infrastructure. We have an 890 square mile site with a couple operating reactors, advanced test reactor, the transient test reactor. We have hot cells. We have a lot of physical infrastructure. We're connecting that up with our modeling simulation, combining experiments and simulation to get the best possible results out of investments made to develop nuclear energy.
I think one of the first reactors ever was here, right?
Yeah, so the first reactor that actually generated significant amount of electricity was here. It's called EBR-1, Experimental Breeder Reactor 1. So that's about, 40 miles west of here?
Oh, wow.
Yeah, and so that started up in the early 50s. And we've had on the site about 52 operating reactors. There's 4 operating reactors right now. And we're developing more. And it's actually a pretty exciting time for nuclear energy between the UAMPS, New Scale Small Modular Reactor that we're planning for the site, Versatile Test Reactor we're planning for the site, and then what we call microreactor demonstrations on the site. All those will involve a lot of simulation, probably more simulation than's ever been applied to nuclear energy before. And you'll hear today about our expanding our computing systems, adding a new computing center. All that's to support nuclear energy development.
Great. So thank you. That's a wonderful introduction. What's next?
So as far as hearing about the site,
yeah.
What's next? Yeah. Well, maybe I'll hand this off to Eric. He'll introduce himself and talk about our computing capabilities and computing plans that we have.
Great.
So.
Come on in, Eric.
Okay, my name's Eric Whiting. I'm the Department Manager for the High Performance Computing and Data Analytics Group. I'm happy to have you here and share part of our story.
It's great to be here. It's my first stop on the Grand 2018 HPC tour.
Yeah. We're passionate about modeling and simulation. It's an important part of science. Just as the commercial industries use modeling and simulation to make better and safer products, we're using modeling and simulation to make enhancements in energy systems. Modeling and simulation requires a computer and then a way to view the results of what you're seeing, or a visualization. Our current computing capabilities include about 50,000 cores, 50,000 processors.
That's a nice chunk of processing.
Yeah. Those processors are highly utilized, they're oversubscribed, they're constantly helping us solve problems and answer questions that we can't answer any other way.
And I think you have a system on the top 500, right?
Yes, we do.
The Falcon?
Falcon is on the top 500, yes.
About 143, 45, something like that?
I think it started at that level. Right now the current list lists it down in the 200s.
Well, we're about due for an upgrade.
Yep, yes, we're due for an upgrade.
I mean, you can't be dawdling in the 200s in the list. I mean, you're Idaho, come on.
Yeah. There's exciting things happen that we are due for an upgrade, and next year we will have a new computer that will be much higher in the list.
Okay. Are you going to GPUs at all, or other accelerators in the next edition?
We have some capability in GPU that we're starting to leverage, but the majority of our work is CPU based. The majority of our codes work best on CPUs.
Haven't been ported over yet or optimized for accelerators?
They have not.
Okay.
We do. There's active work in that area,
sure.
And we anticipate that being part of our portfolio moving forward, but the majority of our workload works very well on CPU platforms.
Okay, so. Good stuff.
I guess one of the reasons we're in this facility right here is high performance computing and data analytics and science generates a lot of data.
Oh yeah.
And to understand that data, oftentimes you need to use tools like visualization to view it. There's a team of researchers here in this facility that have taken virtual reality and used virtual reality to help analyze and synthesize large amounts of data. So where we're going next is we're going to go into the virtual world, a virtual world of material science. We'll go into a virtual reactor control room. We'll go in And then later we'll go inside a nuclear reactor and show you kind of the workings of the reactor from a physical standpoint as well as the physics. We can turn on kind of the invisible things that you don't see with the naked eye inside the reactor.
Oh, wow, that sounds fantastic.
Looking forward to taking you there.
Well, buckle in, everybody. Here we go.
So my name is Thomas Chevchik. I am a visualization engineer over here in K's AVL lab. And what we're looking at here is 42 gigs of data, of graphite data, that we did some scans on, X-ray scans for a volume visualization. We use GPU processing to basically render this image so you can interact with it in real time.
So when you say graphite, is this literally a piece of graphite?
Yep. Mm-hmm.
Okay.
Yep. So we can interact with it in real time.
Oh, wow.
Some of the unique challenges of this, like I said, is 42 gigs of data. And so we can't push that much data into a typical GPU card. So we used some sophisticated algorithms to be able to get around that problem.
You reducing the data or compressing it?
We are subsampling it, but we can also increase dynamically the sampling rate depending on what areas you want to view through it.
42 gigs in this. That's big.
Graphite is a real important material for us for reactors. It's used as a moderator in high temperature reactors. So we do a lot of research on graphite.
Okay, that makes sense. I
We
mean,
radiate different samples of graphite we radiate in our reactors. We investigate the material properties because there are several future reactor concepts that use a lot of graphite. So it's very important material for our research.
okay, so how would someone use this simulation, Tom?
So we use this to analyze, for this particular data set, we use it to analyze pore structures. So we have a transfer function over here where we can actually extract pore structures from it and visualize basically the channels going through it. And also we can do a time series through this to basically see how much it degrades through irradiation.
Okay, okay.
So we can tie in simulators, we can put a gas through it, see how the gas distributes through the porous structure of this graphite, and do other simulations and that kind of nature, material science research on it. So,
Wow, that's pretty impressive. So where's this going in the future, your capabilities?
So we're planning on using this for big data, for other big data samples. And this is still an ongoing project that's still in development. We hope to actually tie this into other simulators we have here at the lab, for example, Moose. And we want to basically...
What's Moose?
Moose is a analytic mathematical modeling software that that has been developed here at INL.
So we've got simulation codes that simulate the structure and behavior of graphite under irradiation and temperature. So Moose is a framework that supports the physics simulations, finite element or other forms of physics simulation. So it's a framework that those can sit on top of. So the physics simulations are done with that. You combine with data to inform those simulations or to validate those simulations. So that's why, looking at this data is so important, to compare it to actually simulated data as well.
But also to be able to visualize it, because it's kind of hard to read this in spreadsheets.
Right, and it's a lot of data that when we simulate things. So the whole point is to get to the state that we can qualify that graphite for use in reactors.
Okay. So that's a very important thing.
That's exactly right. So there are definitely standards that have to be established to ensure the graphite withstands the radiation temperature environments.
So again, a very important function. Great stuff. Oh, I have great vision here.
Yep. So you have hand tracking. That's one of the unique things about this project.
I see my hand, yeah.
So see that white button on
Yes.
the wall? Go ahead and reach out and just press it. So this is full control room Palo
Wow.
Verde is upgrading. So you see those panels over there.
Yeah.
We're actually using those to upgrade that. So this is basically a simulation, a CAD simulation of what the upgrades should look like or what they want it to look like. So
Wow.
instead of the analog kind of switches displays, they want to put in those big digital displays. An interesting thing, so you see that man and woman over there. The man
Yes.
represents the tallest 1%.
Okay.
And the woman represents the shortest 1%. So you can actually see from a human factors perspective of how well these people can reach these panels and switches.
So ergonomics.
Ergonomics, yep.
Wow. This is just for the viewer at home. This is incredibly lifelike. I mean, it's not rendered out to be ultra real, but the proportions are right as I move around. I can see my hands as I hold them out. And just how complex, how deep is this?
Well, right now it's just basic interactions.
Okay.
For example, those buttons you can press, those are just to teleport you because we don't have the physical space
Sure.
for you to walk around in it. But every time we have somebody come in here, they always want full interactions and want to cause a nuclear meltdown.
Yeah, that would be the next, that was what I was going to ask next.
That'll be the next step. So
Because what can I play with here? What can I,
Now, we do have at INL a simulator lab, HSSL, that has a full control room simulator that's full of those panels, those new
Wow.
digital panels. So you can mock up a full modern control room there. And
but a simulator like this?
well, no, it's actually the
It's actually
actual
physical?
panel, so you can go
Okay.
and push buttons and click things in that.
theoretically, we have the capability of hooking it up to a back-end simulator, but we just haven't had that.
Well, that would be quite a bit of work, I would imagine.
Yep, exactly.
I mean, that would be a huge amount of work. This is incredible.
So you have another button right behind the chair.
Just look
So
over
just
the
take
chair on
a
the
few
right.
steps. Take a few steps forward.
Forward.
Your left.
Yep.
Right, that chair right in front.
This one?
No, the
Other
next
one.
Oh, the other one.
Yep. There's a button right.
Oh, I see it. Just pressed a button.
Yep.
Oh, now I'm right here.
Yep. So you can get a detailed look at all the different components.
Oh, wow.
panels and instrumentation that they have in a nuclear control room.
You know, the video isn't going to do this justice, but I'm standing here right next to the tall guy, and he's not all that tall.
Yeah, it's not that bad.
6'1", 6'2", maybe?
Yeah, that's probably about right.
Okay, and I'm looking at
So you can see
all the...
traditional style controls. Mm-hmm. And I don't know, can you walk over and see the new digital camera?
Yeah, it's to the right.
It's to the right.
Yep.
Yeah.
So
Ah, where the
actually,
guy is.
You can touch the big black one, and you should be able to turn it on as just an example of a
Go
basic
up
interaction.
higher,
Up higher?
Yep, the big one.
I'm in your way here. Go up. The panel. See
Yep.
that back panel?
Yep, just touch
Above your hand?
Yep.
Oh, there we
That's
go.
the new style digital display.
Yep.
Wow,
Some perspective of difference.
quite a bit of difference. This is incredible. We're going to need some more water in here, by the way.
Yeah, right.
Yeah, I'm seeing the water levels at 0. I think that wants to be more. Yeah, just from my limited knowledge of nuclear physics, I think you're going to want some water in there and some freed water flow. Just saying. But this is fantastic. I'm really impressed. The guy's got a little flag on his arm. That's nice. Nice touch. Well, it looks like I should be able to feel these things.
Yeah, I know. So there's another button if you want to go to a different area.
Sure.
I think it's to your left.
Okay. Here it is. Okay, so I moved over to my left a bit. It's another of your digital, the new digital representations. Boron dilution system control. How we doing on that? Looks okay. I mean, could be better. Could have a little bit more. We're at about 0.5, 0.6. I'd like to see us closer to 100 up there, but oh well. 113.6 degrees, that's okay. That's fine, right?
Yep.
That's good. That's a good number.
Dan, you have to let me move the camera towards you.
Oh yeah?
Yeah.
Go ahead.
Your camera's going to be on you now, so now be a reactor operator again.
Let's go there. Gonna probably want to scale that up. Not liking how that's looking. Okay. Temperature, I don't know, 115, is that okay? Let me knock on that a little bit. Yeah, okay. Yeah. Boric acid blender online, okay. Free water temperature, 63.8 Fahrenheit. I'd like to bring that up a little bit. I don't know if that's, just seems low to me.
I think we need to send you to school, Dan.
You think?
Yeah.
I feel like I have a feel for this though.
I'll talk a little bit about what the Advanced Test Reactor is. So it's one of just a few research reactors, high-power research reactors that we have in the U.S. And so ATR began operations in the 1960s. It's used for material and fuels irradiation. So
Okay.
we do a lot of advanced fuels, advanced materials. And
So is this essentially seeing how materials and fuels stand up to irradiation?
right. So-
Vast amounts of radiation?
yeah, so you want to irradiate them before you actually would use them in the reactor.
Some things
So-
get brittle, some things...
Yeah, so as you irradiate things, you get radiation damage. You get, for fuels, you get fission product buildup. These are generally at high temperatures, and so we've been irradiating fuels for light water reactors, our current operating reactors with new fuels and new claddings. We've been irradiating special fuels for high temperature gas cooled reactors, so-called TRISO fuel particles, and also metallic fuels that would be used in fast reactors. So it's a very flexible reactor, as you'll see when you go through the visualization, see the core. Very unique serpentine core design. I think one of a kind reactor in the world.
Oh, really?
The maximum operating power is 250 megawatts. It usually operates at less than that, but can go up to 250 megawatts. And when you see the serpentine core, you can control the power in each lobe. So it has a lot of flexibility. So it's a workhorse reactor, runs as much as we can run it to get research results out of it. So steady state, generally steady state operation.
And for all of you looking at going at exascale out there, maybe you want to talk to these guys because they've got the power. How portable is that? You get that next to a data center?
Yeah, well, not this reactor, but we're working on reactors that would be great for data centers. We call them microreactors.
Oh, really?
So these are, the thermal power in this reactor is 250 megawatts, and the control room that you were just in, that's for, a gigawatt class reactor. We're looking at reactors that are a few megawatts.
Oh, wow.
And so you could combine a few of these and be perfect for a data center.
You know what's interesting? I just interviewed on our Radio Free HPC podcast a guy named Mark Fernandez from HP,
Right.
and they just put a cluster up in orbit, and putting a real supercomputer, a big supercomputer in orbit with a power source like yours, that'd be a big win.
Yeah, and we are working on space nuclear power. We've done that for a long time, so definitely very flexible. And the reactor designs we're working on, and be a very good application. So I'll
Very
let
good.
Eric walk you through the reactor here.
Wow.
So Dan, let's stand kind of in the middle here and let me
Okay.
flip this.
I'm afraid of bumping into it. It's so real.
Yeah. I need to stand kind of to your right. Or
Okay.
To your left. No, you're fine.
Left,
You just
okay.
stand there. Let's see. So this is the core of the
This is a reactor vessel here.
This is the vessel. Yep. And as we get close to it in the cave, we can actually kind of go inside.
Oh, wow.
So you're now kind of in the operating area. The fuel is down here in the bottom.
Okay.
And I'll remove some parts so you can see the fuel. But first I want to kind of give you an idea of in this virtual environment, we're going to zoom into these gears just to give you a sense of how, if you were training someone in operation or maintenance, you could kind of give them insights into what
into what everything
what
looks
the
like.
bearings or what the pieces are or things like that. You can.
Yeah.
And your head is tracked, so let's do this. Let's go over. I'm going to go to this. Let's go to these pipes. See the pipes on the
Yeah.
right here?
Yeah.
Go ahead and just take a step underneath them and a step around them, and you can.
Oh, it's moving.
Yep, it goes with you. It's kind of proportional to your motion.
Wow.
It's immersive. It
that
tries to
is-
immerse you inside the reactor.
That is outstanding.
Okay, we're gonna now. So come back to the side here.
Okay.
Let's do this. Let's turn off. Let's turn off some components of this facility. So.
Okay.
First, what I want to turn on a dialogue and we're just going to turn pieces off here.
Okay. So we're getting down to the engine block of this thing.
Yep, exactly. It's a good way to. I'm going to zoom out or change the scaling a little bit.
Okay.
The fuel is the serpentine blue that kind of loops around.
Okay.
The holes, kind of the holes in the little ports, are where we can put materials and do material science work.
Ah, okay. This is what machined uranium? Processed machine, the blue processed machined uranium to fit exactly into that shape?
Yes, it is.
Okay.
Yeah, there's uranium fuel plates
Okay.
in that blue fall, in that blue aura.
Okay. And then you're saying you could put in these things for test?
Yeah, we call those flux traps. Those are each of those lobes you can put radiation experiments. You see there's actually 9 of them.
Actually, right down in these holes.
Okay.
These larger
They
openings.
look empty here, but they usually are occupied with the radiation experiments.
Okay. Okay.
In addition, there's smaller ports. These smaller ones also hold
Okay.
experimental stuff. And the large cylinders you see around the outside are
Yeah.
that's what provides the flexibility in how either absorbing or reflecting neutrons.
Ah, okay. So, I mean, does that control the reaction,
It does.
essentially?
Yeah, that's how you control the reaction. You can see how they're all the way around the core. So as I mentioned, you can control the power in each lobe separately by the different control rods. So you can have like that upper right one operating at a much higher power than the lower left, depending on what
Really?
the experiments need. So it's
Okay.
Very flexible reactor.
Because old school reactors, you just kind of rammed
Yeah,
the control rods into the core, and
Right. So
it was.
those are power reactors.
But this is much more
Designed to be very
sophisticated.
Flexible for radiation experiments.
Okay.
Okay, now I'm going to turn on an analysis tool. I want to turn on a isosurface. And I need another button. Oops, wrong button. Locator. Now I'm going to turn off some pieces of this but we'll leave this out. We'll leave this outer part
This is
on
a
for now.
pretty good user interface. I've had home theater systems that were worse.
So now I'm going to turn on an isosurface that was generated from modeling and simulation, a surface of constant flux, neutron flux. And let me switch the color. I'm going to switch a color briefly. And as we stand back over this direction,
Okay.
and we'll put you inside. So this is the invisible surface that represents the energy. This is, if you will, this is
wow.
kind of the invisible part of the nuclear reactor.
This represents the neutron population. So the whole reason we operate the reactor is to generate neutrons to radiate materials. This is a simulation showing we call it neutron flux, but you can think of it as sort of as neutron population
Okay.
representation in the core.
Wow.
And as if we wish to, you can even step inside this. Let me zoom this up a little bit, and try not to do it too. You should be able to step inside that as well.
Describe what I'm seeing the green,
It's another
These
different
are
level.
contours
another level of energy,
of neutron
and then another level.
getting higher. I think
In the blue.
are probably higher as you
Yes.
get towards the center of the core. Now you're close to the wall.
Yeah, blue is as deep as I can get. Blue, green, and then the red.
So when you get to the center of the reactor, that's usually where the fluxes are the highest.
Wow. This is an incredible
You can
visualization.
also see how the You see how the neutron flux contours go around the control neutrons as well. So how those influence it, you can see that very readily here. And you see where the different, those circles are where the different boats are, I would presume.
Yes.
It's impressive, very impressive.
So again, this is the overlay of kind of the, if you will, the physics and the physical. That's kind of, again, I turned on the vessel just to give you a reorientation.
So we're way deep.
Yep, we're way inside it. So if you stand back over here, the grid lines will disappear and you're kind of back into where you started.
Camera view, there we
Yeah.
go.
Of course, the camera view is going to look a little fuzzy because the camera's not wearing 3D glasses right now.
I'll see what I can do in post-production.
Okay.
Might be able to clean it up.
So,
But yeah, the camera, you're not getting what I'm getting, and what I'm getting is pretty fantastic. Wow. The detail is incredible.
gives you a good view.
Yeah.
Actually,
And physically, how big is this?
the core, I think, is, what's the dimension of the core? 6 feet across?
Yeah,
Okay.
it's on that order.
40 feet top to bottom on the vessel.
Okay. And it looks like, what, probably 20 feet across on the vessel, 20 feet diameter?
I can get you.
That's okay. Yeah, I'm just thinking in case I want to make one at home. What do I need to go down to Home Depot and get?
Yep.
Probably
go
that heavy gauge.
I guess go ahead. If you wish, you can walk right in the middle of it again.
Wow.
It's getting further.
And the detail is just incredible. That's spooky good.
So Eric will talk a little bit about the facility that we're building to house our next reactor.
Computer.
Sorry.
Next, yeah.
Well, virtual reactor maybe, but next computer and office space. So it's an indication of how important it is that we're building a new data center to house this. The computers that we have here that Eric's responsible for are used around the country by industry, universities, and national labs. So they're heavily used, heavily subscribed, and so we're expanding in capability to support nuclear energy. So Eric.
Yep.
Fantastic.
Come back.
Let's jump
see
in.
if your head tracks again. Hopefully your head is. Yep, your head's tracked.
Okay.
So, kind of in the middle of the screen will work.
Okay,
I
got to get one side or the other in order to let the camera get. If you could throw it over here.
Okay.
Are we in? We got it in there? Okay.
If I stand over here, does that help?
That's fine. Yeah.
Okay, so the new facility from kind of a bird's eye view, on the right side there's office space for about 200 people,
Okay.
including an auditorium here in the front for meetings and conferences and training.
Sure.
The left side is where the data center is. The computer will live here, and then you can kind of see depiction of cooling towers and a generator and transformers on the back side.
We're looking at liquid cooling for this one?
Yes, we do.
Good.
Water cooling for most of the systems. Let's go inside Let's go inside the front door of sorts. Let's just. I'm zooming a little bit bumpy.
Got some good shock absorbers down below.
Yep. So we're now inside. We've. I guess as you first walk in the door, Dan, you'll see. I'm going to turn the whole building a little bit to the. Oops, we flew into. We got lost. We really got lost here.
I'm going to pull it back. Here we
Now
go.
let's just punch through. This is the entryway. Mm-hmm. Stand closer to you. As you go in the entryway, there's a viewing area where you can see a couple racks of computers. Mm-hmm. Kind of in the center screen here. And on the right, you see kind of the place, the people side of the facility.
Sure.
Let's first go into the people side.
Okay.
The view is tracking your head, so wherever your head moves, the screens are redrawing. That's why it bounces a little bit as you move around. There's a staircase here, and then around the side there's these working areas.
Okay, good.
I guess I need to put it on the screen here. And kind of a traditional work area, but with some innovative kind of openings and ways to get people to collaborate. The data center, let's go back to the data center facility now. We're going to go Superman over the top.
Okay.
Let's start at the cooling towers on the back side.
Those are good sized. And those are in scale with the building.
They are.
Okay. You're going to be processing a lot of heat.
They're like little buildings themselves.
Yeah.
The transformers and generators on this side. The loading dock is kind of off to the left here.
Okay.
I'm going to take you into the mechanical space first. As we go into the mechanical space, you'll see some pumps and chillers. There's a lot of piping in here, but the piping has been reduced to these single lines. It's been reduced to single lines, so you can kind of see the rest of the equipment.
You're using direct attach water blocks on CPUs and things?
The new systems will be room neutral, so the cooling will be all embedded within the racks. Let's go into the racks. So this is a little bit harder to see because there's so many racks here, but these systems are envisioned to. There's no air cooling. There's no computer room air conditioner units in this part of the facility. Each of these racks will have water that feeds it, and then the water will either cool through rear door heat exchanger or through direct on chip, like you're referring to.
Yeah, I'd probably suggest direct on chip because you get more performance out of it, but rear door's pretty good these days too.
Yep. A lot of systems use a hybrid of the two.
They do.
So some of the newer processors require onboard chip cooling because of their power density, their thermal limit is
and
such.
that's a ghost of Christmas future. That is only going to go up as the process rate size goes down.
Yep. So that's kind of the orientation. That's kind of a view of the facility, and I hope.
How big a system are we talking about, or do you know?
We're not certain yet. Our systems are typically, I guess the first system we envision going in will be approximately 20 racks of equipment.
Okay.
Maybe 5 petaflops in performance.
Okay, that's good sized.
Yep.
So that's about a 5x over what you're doing now?
It is. It's 5x over Falcon.
Wow. What's the timeline?
About a year from now.
For the building and everything?
Yes.
Wow, you move pretty fast up here.
When we walk around the corner, you'll see the building is starting to get closed up. And
you could even get the permits for this in Oregon or California in a year. You gotta love Idaho. 80-mile-an-hour speed limits and quick building. This is fantastic. This could be a great center.
We have some really good partners. We have really good partners that are helping us do this work.
Oh, that's great. I assume the state's in on this with you?
The state is one of our key partners, yes.
Yeah. This could be quite the magnet for Idaho tech education and the entire industry.
It will be.
That's fantastic. Very good. Very cool stuff.
Let me talk a little bit about the universities. Eric and maybe we both can talk about that. This building, in fact, is actually funded by the state to work with primarily state universities.
Okay.
We've got 3 universities at Idaho State University, University of Idaho, and Boise State University that we'll be collaborating with this facility called the Collaborative Computing Center. So purposely to focus on not only research but also education and connection with the state universities. It's a big part of what we do. The building that you're in, Kay's Center for Advanced Energy Studies, also connects with those same universities. So a big presence here of connecting within the state and providing resources and capabilities and connecting them to the research. For INL, it's important to have a pool of talent.
Yeah.
Both universities, faculty, and obviously staff that we hire in.
Sure.
We're trying to build that pipeline within the state, those connections within the state. We've already got quite a few connections on computing with the state universities. Eric may want to talk a little bit about that, but this facility will definitely enhance that greatly.
That's fantastic.
I guess one thing I'll briefly highlight is another partner with this Center for Advanced Energy Studies is University of Wyoming.
Oh, really? Okay.
I guess your road trip is taking you
I'm
to
going through Wyoming, going to hit their supercomputer center.
They're friends of ours.
And I guess another unique thing, another unique capability that Wyoming brings to the partnership is Wyoming has a similar visualization facility to what we have here at INL.
Oh, they do?
And so one of the potential things that we've investigated is software that would link these virtual environments together such that you can virtually be in the same facility and exploring the data together, but yet you're demonstrated by distance, or you're separated by distance.
Do you have a good low latency link with them?
We do.
Okay. So you could almost cluster over that amount of distance on the visualization.
The visualization will work over the link we have, yes.
Wow. So what are we looking at
So
here?
you're now seeing the build out of the collaboration computing center that we saw in the cave, the virtual version.
The one that I was just inside of
Yeah,
virtually.
So, what you're looking at, the upper floor will be where those pods are. You can see there's maybe, you can see the walls coming up now. I guess there's maybe 4 pods there. Can't quite see the staircase down below, but you can see the lower floor. The data center is on the other side of the building. So you're looking at primarily the office spaces that will be on the first and second floor. So they started building this a few months ago, making good progress. This should all be closed in. You can see over here on the left, the walls. Those should all be up in a few weeks. And once they get it closed in, they can start finishing out.
So you have a closed shell before winter really hits.
Yeah, they're targeting by the end of the month to do that.
Oh, wow.
And then we're expecting to start moving in a little bit less than a year.
Wow.
And start building out the computer systems in about a year.
Okay.
So it still takes a little while, but a little over a year and a half or a year and a half or so for the building is pretty good for a building like this.
That's pretty great. And so you'll be doing your top 500 runs in probably, 2 years?
Yeah, it should be the June, not next June, the following June will be the first top 500 the machine we'll have here we'll go into. Roughly 250 people working in this building when it gets done, just to give you some idea.
And of course, you're keeping this facility going as well.
Yeah, K's will stay going. We have a computer data center over in our other engineering research office building. That will be shut down. We'll move those 2 computers. We've got 2 computers over there. We'll move over as well as our new computer. It'll be in this.
So you've got quite a bit of floor space in the data center.
Yeah, there's plenty of space. The new computer won't take that up. We've got space for, as we mentioned, working with universities for them to put computers in here as well. And we're talking actually to industry, what the industry connection is. The nuclear industry themselves don't operate large data centers or computing. It's not their business. So we collaborate with them, provide computing resources here, and we're hoping to jumpstart and move the nuclear industry into advanced computing. So get them in here, and at some point, perhaps they will stand up their own data centers or lease time in cloud or other purposes like that. So
well, in some ways, you might become their cloud.
we could. There are, a lot of that data is export controlled, proprietary, so it's going to be carefully managed.
You can't put that up in AWS.
Yes. There's the FedGov cloud that we've been talking about using.
Yeah.
So it's possible. It is possible actually to do that, and we're looking into that as a capability. But
you've got so much data to move, though.
yeah, there is a lot of data, that's for sure.
Yeah. Oh, this is fantastic.
So anyway, you're at the very beginning. So hopefully you can come back in a year or so, and it'll be up and running, and we can
Get a tour of that one?
system. Yeah.
Then you'll take me in virtual reality through the next one.
That's right.
Thank you so much.
And so we're glad to have you visit. Hope you got what you
I did.
some good information.
I got so much more in
and
that.
Got the message of how we're connecting high performance computing to nuclear energy, which is what we're all about here. So
Fantastic. Thank you so much for your time.
thank you.
I'm going back to where